Good. So, good afternoon, everybody. I hope all of you are fine, are physically and mentally well, taking care of yourself and each other in these difficult times. So today our guest is Professor Konstatin Batygin. He received his bachelor's degree in astrophysics from the University of California in 2008, before pursuing graduate studies at the Caltech, where he currently holds a position as professor. When not doing science, he enjoys playing in his rock band, the Seventh Season. Is that?
That's true.
Great. Good, good.
Yeah.
And well, Batygin has authored almost 100 scientific publications, so he is very active and very well known from his works. And the subjects of his works move from hot Jupiter structures, the orbital architecture of exoplanets, Planet 9, and the distant solar system. So today, Professor Batygin will give us a talk on injection of inner world cloud objects into the distant Kuiper belt by Planet 9. So please, Konstantin, the podium is yours.
All right. Thanks so much, Othan. This is a great pleasure for me to talk to all of you guys virtually. And really today I want to talk about a couple different themes that I've become quite interested in over the last few years. And with these kind of like over Zoom type talks, it's always more difficult to gauge the extent to which we're all engaged. So if something does not make sense or anything of the sort, if at any point you have a question, please don't feel don't hesitate to just interrupt and ask a question. I'm perfectly happy to do this more of as a discussion rather than just the usual kind of talking into a screen. So I want to really today begin with a discussion of Planet 9, and this is a problem that I've become quite obsessed with, together with my partner in crime, Mike Brown, as well as others. And I think to really gain a full appreciation of how far the field of trans-Neptunian solar system, our understanding of trans-Neptunian solar system has come over the last 3 decades, it's worthwhile to remember that the first Kuiper belt object was discovered, I guess, back in 1992, really 1930, because Pluto was the first Kuiper belt object discovered, but the first sort of small one was in 1992. And since then, the kind of relentless observational mapping of the outer solar system has led to a pretty clear picture of what the outer solar system is beginning to look like. So this little animation is outdated now. It's from a few years ago, but it just shows you kind of the vast diversity of architectural structure of what's going on beyond Neptune, right? There are so the discovery of this population of icy debris has right away led to kind of a rewriting of the solar system's early dynamical evolution, right? So the pre-Kuiper belt, the sort of standard model of the solar system was one where the planets just form where they are today, and you could reconstruct or imagine to reconstruct all kinds of things about the early solar system. That's not true, right? With the discovery of the Kuiper belt, it became very clear that the planets migrated in a violent fashion in this class of early instability models that are now kind of collectively called the Nice model. Now, as far as this rewriting goes, the story is pretty consistent. I think pretty well worked out today. In essence, the planets all start out in a more compact configuration encircled by a disk of icy debris, as shown here. And then as the planets begin to eject these debris, which form the Kuiper belt, right? The planets also jump to their current locations and then circularize sometime later. So this, what I'm showing here, is a visualization of a simulation that I did back when I was a graduate student, but this is just one of kind of many realizations of the NICE model. There's been, in fact, considerable progress over the last decade and kind of getting the details right of the final stages of Neptune's migration. This is particularly work that David Nesvorny and company have done, where they've been able to really get at how Neptune finished its migration, the coarseness, and all of this stuff. The reason I'm showing you this is that what I really want to drive home is that this is how the Kuiper belt formed, right? The Kuiper belt is a remaining, remaining speck of this original population of 20 Earth masses of debris that got ejected from the solar system within its first 100 or so millions of years. So the NICE model has been really successful in reproducing much of the structure in the proximate part of the outer solar system. But something we noticed back a few years ago now is that if you look at the most distant orbits that comprise the Kuiper belt, there's an interesting kind of hint, an intriguing pattern that emerges. So this, again, animation is a few years old now, but it kind of shows you where the Planet 9 story, at least for us, began. If you look at these objects that whose orbital periods exceed about 4,000 years, they all appear to lie in the same plane and all appear to kind of point into the same direction. Since then, the number of these objects has gone up by a lot, right? This is the data set has more than doubled. It has in fact almost tripled, and what we see is actually an intriguing pattern. If we just look at the orbits, at face value, there's a clear kind of propensity of objects to cluster depending on their current dynamical stability. So again, these are all of the objects in the distant solar system today that have orbital periods greater than 4,000 years, semi-major axes greater than 250 AU. And what I've done here is I've labeled the different orbits according to their dynamical stability. So the objects that do not diffuse at all in semi-major axis are shown as the purple orbits. The ones that diffuse very rapidly and are kind of on their way out of the scattered disk are shown in green. And the ones that are sort of in the middle, that diffuse a little bit over the age of the solar system, but not too much, are shown in gray. So kind of without doing any sophisticated statistical analysis, you can tell that the green orbits are all over the place, and the dynamically stable kind of large perihelion orbits are well clustered together. So this is pretty weird, and you can't really attribute this to any event that happened early in the solar system's lifetime, because if you were to then just plop down these, orbit, the solar system as is, and just evolve it with the 4 giant planets, due to the secular precession induced by Jupiter, Saturn, Uranus, and Neptune, the orbits will kind of be spread out into an incoherent structure on a timescale of a few 100 million years. So if this pattern of clustering is real, and indeed I do believe it is real, then something is holding it together. Something is holding this pattern together, right now, so to speak. So what is that? Well, what we've been talking about for sort of the last 5 years is that this pattern of orbital clustering is best attributed to the existence of an additional long period giant planet in the solar system. Now, if such a planet exists, it naturally drives a multitude of dynamical effects. First and foremost, and this is what you're seeing now is a simulation of the outer solar system kind of over the 4 billion year lifetime of the sun, or it's 4.5 billion year lifetime of the sun, where Uranus and Neptune are here. And as you saw in the beginning, all the Kuiper belt orbits start out in an azimuthally uniform manner, but we are labeling the ones that are kind of short period with this green with these green orbits, and the long period orbits are labeled in this blue color. As dynamical evolution ensues, what happens is that the orbits that are collinear, right, in terms of longitude of perihelion, with the orbit of planet 9, which is shown here in pink, preferentially get ejected from the solar system. The way that this works is actually there's an eccentricity maximum that you go through when you're aligned in perihelion with the orbit of planet 9, and by driving the perihelion into the orbit of Neptune, these objects get cleaned out because Neptune scatters them away. So you kind of, just from kind of a stability point of view, in time, carve out preferentially orbits that are anti-aligned, tidally anti-aligned with respect to the orbit of planet 9 in these simulations. There's another intriguing effect which happens, at the same time, which is of course that planet 9 modulates the orbital eccentricities of Kuiper belt objects up and down. So the process of perihelion lifting, right, taking the orbit and making it detached from Neptune and thereby making it stable, in this story is very much the same process that leads to orbital clustering, right? The two things are conjugated. Simultaneously, there's a parallel effect which happens in the node inclination dynamic, namely that planet 9 sort of tilts the distant population of the solar system into by maybe about 10 degrees, and we sort of see that in the data as well. So to kind of give a update on where we thought the situation was back in 2019, we ran a few thousands of these simulations and did our best to sort of match them to the data to the extent possible, and came up with what we thought was a best fit planet 9, which is an object of about 5 Earth masses in a period of about 10,000 years. That translates to a semi-major axis of about 500 AU and a lower eccentricity than we originally anticipated. So we wrote this review article where we argued that the eccentricity of planet 9 is maybe about 0.25. Now, it would be unfortunate if I didn't kind of mention the way to kind of attack all this, right? Because after all of this story, this entire kind of planet 9 hypothesis is predicated upon this clustering that we're seeing being real, right? Or being at least statistically significant. So obviously, if you want, the thread to pull on, if you want to kind of see, take planet 9 to court, if you will, is to argue that the clustering that we're seeing is not real. So there has been a few papers in the literature over the last few years that have done this analysis, and the basic idea, culminating in the recent paper by Napier et al., is that if you do the exercise of asking, of doing survey simulation, where you take the pointing history of some survey and asking, could you tell with the given survey if a population is clustered or not? The answer is no, right? So the individual surveys that have been conducted over the last few years basically do not have the capability to resolve the question of, is this clustering truly there or is it not there, right? So something that Mike and I have done as a way to circumvent the survey simulation approach is to do what is called observability mapping, and that is to an exercise where you forget who discovered what on the night sky and attributing discoveries to specific surveys, and just say, okay, if we take the entire sample of detected Kuiper belt objects that have ever been detected, then there's information there, right? Like if there's an object with some array and deck and some magnitude, right, some brightness, that means somebody looked into that spot on the sky and was able to discover an object of such brightness or brighter. So then you can kind of use the entire catalog of discoveries to construct a bias function for each Kuiper belt, each of these long period orbits individually. And through this process, ask what is this sort of false alarm probability that we're dealing with. So we've done this exercise a couple times now, and to update you on where things stand today, if we, even if we just limit our sample size to only the stable Kuiper belt objects, then the false alarm probability of clustering clocks in at about 0.4%. So in other words, there's a 0.4% chance that the alignment that we're seeing is by coincidence. So that's kind of where we are when it comes to the statistics of this. So I would argue that this is interesting enough to pursue further. And the problem that we encountered during the pandemic in thinking about how to take the Planet 9 hypothesis to the next level, if you will, is to realize that the first couple slides that I showed you in this talk, right, are missing the fact that the solar system did not form in isolation. Indeed, all of what I've said up till now imagines indeed that the Kuiper belt formed by Neptune ejecting material outwards, right? And that material forms the Kuiper belt, and then something happens to it due to gravity with Planet 9. But of course, the solar system did not form in isolation. The solar system formed in a cluster of stars. This is just one example of a beautiful picture of a star cluster. And we see evidence of the sun's formation in an association of stars all over the place, including in the meteoritic record of short-lived isotopes. So why does it matter that the sun did not form alone? Well, the reason it matters is because this process of ejection of icy debris is actually not limited to the instability itself, which I showed in the second slide, but in fact predates the instability. So because when Jupiter and Saturn themselves, the giant planets of our solar system, form, their conglomeration destabilizes their orbital neighborhood locally. So they begin to scatter debris outwards, right? This is relatively trivial. Now, these debris, as they scatter outwards, do so maintaining, roughly speaking, a perihelion distance that is close to the orbit of Saturn. And if this was all happening in isolation, eventually they would just leave the solar system. But because this is not happening in isolation, because they're passing stars, as well as the tide of the cumulative cluster potential, As these orbits become elongated and develop long periods, perturbations from passing stars can detach them from Jupiter and Saturn themselves, and form this kind of toroidal, almost quasi-spherical cloud of material that both has a high perihelion distance and has high semi-major axes. This cloud of material, which is conventionally called the inner Oort cloud, if Planet 9 is not there, would just sit there forever, okay, and nothing really would happen to it because it's too close for the galactic tide to do anything too drastic to it. It's definitely too close for passing stars right now in the galactic field environment to do anything interesting to it. But if Planet 9 is there, then through the same modulation of eccentricity and perihelia that I discussed a couple of slides ago, Planet 9 would cause some of the at least a fraction of the inner Oort cloud to get re-injected back into the Kuiper belt. So this is what we began thinking about really during the pandemic, and began attacking this with numerical simulations, really to get at the question of, if this is true, right, then what does this mean for the data set? Right? If this is true, this means that the distant Kuiper belt is really composed of two populations. One is the scattered disk itself, material that has been ejected by Neptune, and there's a secondary population of material being re-injected back into the solar system from the outside in. So how does that work? So to do this, we first ran simulations of Jupiter and Saturn forming in the early solar system inside the birth cluster, kind of adopting a birth cluster model, which is, I would say, pretty typical, kind of similar to the Orion nebular cluster. And you know, this was done really to produce a model inner Oort cloud, which you can see on this plot. So here the key features is that you can see a whole bunch of little pieces of debris following the Saturn perihelion line all the way out to 1,000 to 10,000 AU, and then their perihelia being lifted above 40 astronomical units by passing stars, etc. And there's a pretty specific orbital dispersion that these objects acquire. This was really done as a way to produce the model inner Oort cloud. And then we sort of just repeated our usual calculation of Planet 9 induced dynamics to see what we would find. So this is a comparison of the standard Planet 9 calculations where all of the particles were initialized within the scattered disk. That's shown on the bottom. It's kind of the control simulation. This is similar to the calculation you saw, the video you saw a few slides ago. And the top slide shows, for the same Planet 9 parameters, what happens when you source the Kuiper belt from the outside. It's difficult to tell just by looking at it, you know, because there's kind of points all over the place. But I think it's perhaps almost easier to see the difference in effects when you're looking at the polar inclination plot, which is this right-hand side plot where if all things come from within the scattered disk, you get quite a nice forced equilibrium. So kind of things shift to the right in I cosine delta node, and that shifting you can almost see in the in models where the Kuiper belt is sourced from the cluster, but it's much more degraded. And indeed, that's the cumulative kind of the conclusion of this exercise, namely that particles that are injected from the inner Oort cloud do exhibit the kind of clustering that we have come to expect from Planet 9 induced dynamics, but the degree of that clustering is much weaker. And here I'm just plotting the PDFs as a function of the apsidal offset with respect to planet 9 to kind of drive this point home, where the particle is initialized within the scattered disk. The standard calculation is shown as a black curve, follows this almost Gaussian pattern, and everything else, the material that's injected from the inner Oort cloud, as you can, I'm sure, see, is considerably more, a lot more noisy, if you will. So what this means is that if the outer solar system is indeed composed of these two populations of trans-Neptunian bodies, those ejected by Neptune and those re-injected by Planet 9, then really this means we've been underestimating Planet 9's eccentricity over the last couple of years. The reason being that Planet 9's eccentricity controls how clean the clustering is, right? It controls how tight this apsidal, apsidal grouping ensues in the calculations. But if the clustering is in fact being messed up, if you will, by the particles injected from the inner Oort cloud, we actually need a higher eccentricity P9 to explain the data. Now, at this stage, we've only really outdone the proof of concept calculations, and we are still in the process of doing the real estimate, trying to understand how bad this this effect is. Like by what extent is the eccentricity of Planet 9 higher than 0.3? So I don't have a kind of a final number for you, but at this stage, there's a different set of constraints that also come into play, and those constraints come from the fact that Planet 9 also, we believe, is responsible for generating high inclination structures in the distant solar system, and those high inclination structures would be messed up if the eccentricity of Planet 9 gets too high. So, if we end up doing this, kind of chasing this value from two sides. So if I was to guess, I would say maybe the eccentricity of Planet 9 is maybe 0.4 or something like that. And all of this is important, of course, for the observational search that we are conducting. And to kind of summarize these results that I just discussed. Right, if icy bodies injected into the Kuiper belt from the inner Oort cloud by Planet 9 show weaker clustering than those that originate within the Kuiper belt, and if the data is contaminated by inner Oort cloud objects, then the orbit is more eccentric. This was published recently in AppJ Letters, so I'd be happy to discuss the details of that further and invite you to check out the paper as well. So at this point, I want to switch gears a little bit and talk about another project that I've been really excited about over the last year and a half, particularly with respect to the formation of giant planets. But perhaps we can take just a 3-minute break, and I can ask if there are any questions on Planet 9 that I can respond to right away while it's sort of still fresh in our minds. Okay, so if there,
I don't think that there's any question at the moment.
Okay, no, not a problem. I just wanted to kind of ensure I give the give the opportunity. So okay,
Konstantin. So sorry.
Yes, of course.
That's Rogério.
Hey, Rogério, how are you?
How's it going? Good, and you?
Good to see you again.
Good to see you. So just a quick question on when you're injecting things from the inner Oort cloud, how does the flux of comets related to that?
The flux of long period comets. Yeah. Okay, so the flux of long period comets here is really not even part of the story, because the comets are coming from the classical Oort cloud, right, which is further out, and the formation of the classical Oort cloud is a different event from the formation of the inner Oort cloud, right? The outer Oort cloud was made during the was made after the sun already had left its birth cluster. Otherwise, the Oort cloud would have become unbound, right? Just because the passing stars are passing at 10,000 AU or something like that. So, really, the comets are not, I think, are not particularly relevant to this story. Also because they kind of tend to come in with, but now that I think about it, I should not dismiss the comets so readily. Yeah, okay, so to answer your questions, they're not part of these calculations, but I should think more about what they would do if we were to include cometary flux from the classical Oort cloud.
Yeah, because I think Dave did some work on the influence, the effects of Planet 9 in the comets. I don't remember exactly what the results were, but I think there were some inconsistencies depending on how you assume the orbit of the planet.
You mean Dave Nisvorny?
Yeah.
Oh, yeah. I'm quite familiar with that paper. So in that paper, I think the eccentricity of Planet 9 was set to a value so that it would produce the 6th degree obliquity of the sun. And it's a overly eccentric Planet 9, and it's absolutely true. If you make the eccentricity of Planet 9 too high, then you excite the inclination dispersion of the distant belt. So then you create a huge tail of high inclination comets. That's absolutely true. If the kind of update on that part of the Planet 9 story was a paper, I think by Nate Cabe relatively recently, where what they looked at is the flux of high inclination centaurs coming into Neptune and doing their thing. So that paper found the same thing, which is that if you use kind of the original 2016 values of Planet 9 with like an eccentricity of 0.6, then you overpollute the outer solar system with high inclination centaurs. If there's no Planet 9, then you underestimate, like the OSOS sample of those high inclination objects is too high compared to the model. But if you use the new values, the 500 AU eccentricity of 0.25, you basically get it perfectly right. I mean, there's still there's a couple degrees offset in the mean value of the inclination, but actually there's a pretty good agreement there. That's what I was talking about when I was saying that you can't make the E of Planet 9 too high, because then you start to run into the exact problem that you're mentioning.
Okay. Cool. Yeah, thanks.
Okay, thanks, Rogério. We also have a question, a comment by Josué. So please, Josué.
Hi, everyone. Hi, Konstantin. Thank you for the presentation. Very nice work. I have a simple question that is about how you estimate the initial mass in your simulations and how you distribute this mass to represent the Earth's cloud in the simulations. Thank you.
Yeah, so the way that we do is basically, so first of all, the population of debris that initially reside beyond Saturn, cumulatively, we say, is about 10 Earth masses. And by about, I really am using a tilde here. It can be 20 and we'll get the same answer. Then they get scattered away. Most of them actually do not get retained in the inner Oort cloud. The inner Oort cloud capture probability is a little bit less than 1%. Okay. Then, right, some of that material gets re-injected back into the Kuiper belt, but not all of it. So what we've done is basically that, okay, if you count up the probabilities this way, how much mass in the distant Kuiper belt that's observable right now came from the inner Oort cloud? And the answer is 10 to the minus 3 10 to the minus 3 Earth masses. Okay. Now, 10 to the minus 3 Earth masses is a frustrating number because it is neither much higher nor much lower than the mass of the scattered disk. right? The mass of the scattered disk is maybe 10 to the minus 2 in total, but we're only focusing on the very kind of outer edge, right? So it's a frustrating, because we can't say, okay, this is negligible, right? We also cannot say that this is dominant. So it's kind of, it might be a 30% effect when you count up how many of these objects, something like that, maybe 10% effect.
Yes, I guess you might have some work to be done about using the inverse concepts to determine and try to estimate, because if you find all these structures that you're trying to prove, I think it will be very important also to help to expand this even outer solar system structure.
Absolutely, absolutely, yeah.
Thank you.
A lot of
Very
detective
nice.
work. Yeah, thanks.
Very nice. Thank you.
Thanks.
Thank you.
Well, let's see if there are no other questions. I'd like to sort of jump back in and discuss the satellites a little bit, which is a completely, of course, completely distinct from Planet 9, but an equally fun problem. And
Okay.
to kind of get at where we're going with this, in the interest of time, I won't go through every slide in detail, but I will go as far as to say that, of course, the Galilean satellites were sort of like the first thing that was ever discovered astronomically, right? And over the next decade, we're going to learn a lot more about their geology, their geophysics, their missions, both by NASA and ESA, right? There's the Europa Clipper that's going to Europa, that's going to clip Europa. There's JUICE that's going to Ganymede. There's a drone called Dragonfly that's going to Titan, the moon of Saturn. So there's I think quite a bit of renewed interest in the icy satellites, and it's all very exciting. But I would say that against the backdrop of the detail with which we will know, the geology of the icy satellites, our understanding of how they formed is incomplete, to say the very least. I don't want to spend too much time talking about the kind of models that exist in the literature today, other than to note that they kind of fall into two broad categories. One is the minimum mass model, where you say that the Galilean satellites represent kind of the high metallicity component of the initial circumjovian disk of material from which they formed. And you can construct, just like you can construct a minimum mass solar nebula, you can construct a minimum mass, circumplanetary nebula. And this model doesn't work, right? The temperatures that you have inside such a disk are so high that you would not form icy satellites. So given the fact that the minimum mass model produces an overly massive disk, the alternative to this, proposed by Canup and Ward about 20 years ago, is the gas-starved model, where the amount of disk is much less, and all of the solid material from which the satellites form is actually getting captured from the outside and then the satellites form and so on. Okay. I think in 2021, it's interesting to re-examine these models, especially because we are now living in the age of ALMA, where we're actually for the first time starting to see not just the disks themselves, the circumstellar disks, but we are starting to detect circumplanetary disks in orbit around other stars. And the picture that has been painted from these new detections is one that is very different from how we thought the story operates before. This is a simulation done by, what I'm showing the inset is a simulation done by Elena Lega at Nice. And if you have looked at top-down view, you have what looks like a circumplanetary disk. That part is maybe expected. What is really fascinating, however, is that the kind of side view of this story demonstrates that disks, circumplanetary disks, are not fed from the midplane of their parent nebula. Instead, they rain down vertically. So, in other words, when Jupiter is born and clears up its gap within the protosolar nebula, material from the top of the gap will overflow the gap and fall down vertically, kind of like hydrogen and helium rain, if you will. And then, due to conservation of angular momentum, make a disk around Jupiter that then viscously decretes back into the disk, into the parent nebula, causing an overall meridional circulation of gas. If you do not believe in numerical simulations, that's kind of okay. But I'm sorry for that weird slide there. I don't know what happened. But the truth is, this meridional circulation has been detected in data by Teague et al. So this is really the picture that ensues when you're forming giant planets. This story is actually extremely problematic for the formation of satellites. The reason being that even the basic question of how you accumulate enough mass in the circumplanetary disk to form the satellites becomes one that is hard to answer. And that's because dust in the protoplanetary disks, just like, I don't know, dust in the desert or dust anywhere, dust under my bed for that matter, tends to settle, right? And so because dust settles to the midplane, if you're grabbing all of the material that is making a circumplanetary disk from the top of the nebula, it's extremely dust depleted. It's low metallicity gas. And moreover, because there's a size dependence to the efficiency of dust settling, the material that's coming in to form the circumplanetary disk is all tiny dust grains, like maybe 10 microns, stuff that's so small that it can be suspended at the top of the parent nebula basically indefinitely. Then you have another problem, which is that if these grains that are coming in remain tiny, they remain so well coupled to the gas that they decrete along with the meridional circulation back into circumstellar disk. So in other words, you're grabbing kind of some of the smallest, icy and rocky particles available in the parent disk, and if they stay that way, they just get recycled back into the parent disk. Conversely, if they grow, right, and then you have an extreme version of the meter barrier, which is kind of a well-known issue, right, for the solar nebula, namely because circumplanetary disks are so hot and generally, significantly subcaplarian. If solids grow, they will get their orbits will decay onto the planet. So we have this issue. So what we proposed as a solution to all of this, this is work done with my friend Morby. This was published last year in AppJ, is that we said, okay, first of all, let's make a simple model for a circumplanetary decretion disk, which is just a constant m dot model, and see what happens to solids in such a disk. Now, this is kind of the key cool result that I want to emphasize. The equations of motion, right, of a solid particle in a nearly circular subcaplarian disk are very well known. Okay, they're just right here on the screen. You can look them up in the papers by, for example, Nakagawa from 1986. That's kind of a classic reference, or just the Armitage textbook or whatever. So these equations are not only very well known, their consequences are also very well known, because what happens is if you put dust into a disk that's going at subcaplarian velocity, the dust wants to go Keplerian, right? So it feels a headwind from the subcaplarian gas, and so the dust loses energy and angular momentum and sinks towards the star, while the gas sort of moves out slightly. That's the Nakagawa like equilibrium or Nakagawa, right, a steady solution. So that's all well and good, and that's well known. But in circumplanetary disks, we have a marginally different physical situation. And namely, we have a different situation because the background flow of the gas is not only subcaplarian, it is also positive in the radial direction, right? I mentioned, again, if I go back to say like this slide, there's these arrows that signify the meridional circulation, right? As the disk forms, it viscously decretes, meaning it flows back out into the parent nebula. So what the kind of dumb thing that we asked ourselves is, what happens to these equations if VR of the gas is positive? And turns out if VR of the gas is positive, they admit not only a steady solution, they actually admit a legitimate equilibrium solution, which corresponds to an equilibrium frictional timescale. This means that grains that attain a certain frictional timescale, in other words, grains that attain a certain size, will stop moving in the disk altogether. Okay? This is because the balance that allows them to kind of stay steady is the fact that as they're moving outwards as they're experiencing drag with the subcaplarian flow, they're trying to fall in, but the radial outflow from the planet is kind of keeping them confined. So particles, once they grow up to a particular appropriate size, will get trapped in the disk forever. And we think that this is a attractive resolution to the problem of how you accumulate enough solids. That, namely, of course, you feed the disk with very fine kind of particles that are very small in size, but in the disk they grow up to a particular size and then just get trapped in there forever. Now, of course, I'm skipping over a lot of the details here because, as it turns out, the kind of grain growth and grain sublimation cycle play a really important role in maintaining the particle radius at this close to this equilibrium value. But that's not something that I want to spend time discussing, right? Because there's a lot more work that needs to go into this to work out the details of that. So the story that we've come up with, right, is that the disk is fed vertically, the solids accumulate in it, but of course this problem of solid accumulation cannot continue indefinitely, and eventually, right, this disk of dust has no choice but to settle and begin collapsing into satellitesimals. Once again, I'm skipping over a lot of the details, but what we have argued here is that the standard kind of new emergent paradigm of planetesimal formation, which is the streaming instability in protoplanetary disks, is likely not what's driving satellitesimal formation. Instead, we think actually the satellitesimal formation just forms by a variant of what's called the Goldreich-Ward mechanism. The idea being that as the metallicity of the disk increases, just the turbulent kinetic energy becomes insufficient to maintain the dusty subdisk in a puffy state, so it just collapses under its own weight. And we've sort of demonstrated that this happens for if you just kind of allow the circumplanetary disk evolution to run its course. This is kind of a natural conclusion to it. So you form the satellitesimals, and the satellitesimals then have two options for how to keep growing from that point on. They can accrete pebbles, right? The process which is gaining a lot of, again, traction in thinking about how planets form, right? Pebble accretion, or they can grow by mutual collisions among each other. Now, what we have demonstrated, at least in our model circumplanetary disk, is that the process of pebble accretion is extremely inefficient. The reason it's inefficient, because all the pebbles have to be have to basically be at this equilibrium size, right? That's why they are in the disk in the first place. And it turns out that equilibrium size corresponds to a rather low Stokes number. So pebble accretion doesn't work very well. So, you know, if it's not one, it sort of must be the other. And what we've been able to then kind of demonstrate is that if satellites grow by just pairwise collisions, then the calculation is a relatively simple one, right? They just kind of collide until the objects grow large enough to start raising significant spiral wakes in the circumplanetary disk and migrate inward. So you can derive a characteristic mass scale in this theory for satellites just by setting the kind of mass doubling timescale equal to the migration timescale to arrive at a number. When you do that, you know, in a very natural way, you kind of get 2,000 kilometer satellites. This is, again, like, this is just an analytic calculation, so it's not it shouldn't be interpreted as the truth at the detailed level, but the fact that you kind of get 2,000 kilometers naturally from this story is pretty attractive. Okay, I will finish this story about the satellites by just showing you the n-body simulation of our story. Kind of after coming up with all the analytic stuff, of course, it's crucial to test it all with simulations. So I'll again start here. So this is a stage where the satellite decimals have formed, and we begin with Jupiter at the center, a disk of solid debris, which starts out at about 0.1 Hill spheres. The reason there's no debris close to Jupiter is actually because in our model, the conditions for gravitational collapse of solids are not satisfied inside of 0.1 Hill sphere. So satellite, all the solid stuff sort of forms outside of 0.1 Hill sphere. And then we seed this disk also with some baby embryos, which are then allowed to grow by mutual collisions, and then experience type 1 torques with the nebula, which we kind of implicitly assume is there. So as we let this story unfold, what happens is very quickly, in fact, almost immediately after the large-scale formation of satellite decimals, Io forms and attains the real mass of Io. We have here on the right-hand side, it's kind of a logarithmic mass bin of how the satellites are forming. What's quite astonishing is that in the story, there's kind of a natural reason for why Europa is less massive than Io, and that reason is that Io's formation, in fact, messes up the inner disk, if you will. And so as the velocity dispersion goes bigger, right, formation is not as efficient. So in the story, you really reproduce the fact that Europa is a less massive object than Io. And then the formation of Europa further messes up the disk, so Ganymede's formation takes longer, and so on and so forth. So each sequential formation of the satellite makes the formation of the next one happen over a longer and longer time scale. Now, because the thing that sets the terminal mass of the satellites is the coincidence of migration and accretion timescale. Here, migration is an undeniably important part of the problem, and in fact, what we find is that we form the Laplace resonance just in a conventional, conventional way, where it's just type 1 torques that drive it to the inner edge of the disk, and the resonance forms that way. There's a cute result associated with this, namely that if you form the Laplace resonance not by outward tidal migration as proposed by Goldreich 50 years ago or so, but really inwards by type 1 migration, there is both a constraint on the migration timescale that ensues, namely it has to exceed 10,000 years. And the other thing is that the assembly of Laplace resonance really has to happen from the inside out. If you form all of the satellites at the same time and they migrate together, then due to overstability of the 2-to-1 resonance, Ganymede and Europa would not be in a 2-to-1 resonance today. The final portion of the story is, of course, the formation of Callisto, and we think the formation of Callisto largely happens and is largely really triggered by the photoevaporation of the nebula by coincident with the photoevaporation of the protosolar disk, leaving behind just a just kind of the n-body problem in which Callisto forms. And so we kind of argue that the reason Callisto is not in the Laplace resonance is that its formation was delayed until the gas was already gone. And because of that, right, its inward migration happened by planetesimal scattering. The interesting thing is that all of this, I mean, I'm telling you all this as if I'm like, I made it up, from scratch, but I really didn't. I'm just merely interpreting the results of these self-consistent n-body simulations. So the fact that at the end of the day, our model reproduces the masses, both the masses and the orbits of the satellites, I wouldn't say is kind of somehow definitive that this is exactly how they form, but I think this model provides a neat skeleton on which to then build further, because I think this is kind of an attractive paradigm for satellite formation. Okay, it is my clock is showing 1:59 p.m. so I should stop talking at this point and take any questions.
Okay, Konstantin, very interesting presentation. So we are open for questions or comments. Anybody? I have one. Could you repeat your explanation about the Callisto?
Yeah.
You have to impose some delay time. You have to force that.
So basically, here's kind of the timing of the story. Once satellitesimal formation starts, right? Once you make the building blocks, Io forms very quickly. Europa then takes sort of 10,000 years. Then Ganymede, takes 50,000 years, and so you kind of make each one take longer. So there's a natural way in which you delay the formation of each satellite further and further. The reason that we imagine Callisto formed later is because it's not in the Laplace resonance, right? You can, in principle, imagine that Callisto forms while the gas is still there, then migrates in, and then it'll just become the next member of the Laplace resonance. But eventually, however you do it, the gas goes away, right? And when the gas goes away, you still, at least in these simulations, you still have there's enough material basically to form final satellite, which then migrates inwards by planetesimal scattering, and then that reproduces Callisto pretty well. Overall, I should say that there's reason to believe that the entire story, the entire circumplanetary disk story, happened towards the very end of the lifetime of the solar nebula. The reason is that in hydrodynamic simulations, you have to wait until this m dot that forms the circumplanetary disk is pretty low for it to become a disk. As long as m dot is high, you just have a giant envelope because it's very hot. So one kind of, I wouldn't say that this is set in stone, but it looks like all formation of satellites is kind of delayed to the last maybe 0.3 million years of the lifetime of the system anyway. So this is why we imagine that Callisto has formed after the blow off of the disk. Does that make sense?
Okay, yes. So it's not forced, it's natural consequence. Okay, that's the main point. Okay, yep. Okay, good. Okay, anybody else? Any other questions or comments?
I think there was I maybe saw that somebody raised a hand. Maybe not.
I don't see at the moment, no. Okay, so thanks very much. We had 2 in 1, so
yeah,
very good, and very illustrative. Your videos are great, and they help very much to convey the idea. So
well, yeah, thanks very much, and yeah, it was a pleasure to see some familiar faces, as well as meet some new faces. Again. Thanks very much for watching, and don't hesitate to, if you have any questions, just reach out to me directly afterwards over email or whatever, and I'm happy to discuss all these models in greater detail. Okay, good. So thanks very much. And just at the end of our seminars, we have a few minutes for if anybody has